persuasive. Currently provides a more convincing rewriting. Beyond shortening text and transforming my tone, it currently can often help me untangle complicated, hard-to-follow sentences to ensure my points are clear and easy to understand. Make sure you download Grammarly for AI writing assistance. Now go write.
Father knows what I say. Everything I'm wearing, I'm dancing.
And I'm just paying on my car insurance for driving safe. Okay.
Our insurance that flexes with you. Okay. One moment. Okay, let's get started. Aleo Ligares Adrian. Here. Aleo Ligares Justin. Bingy. Here. Francois. Coates.
Here.
Times. Hodges.
Here.
Leave it. Lee.
Here.
Momberg. Momberg is here. Okay. Martin.
Here.
Medina is here. Moreno. Here. Moreno. Oh. Perush is here. Salmons. Wheeler. Here. Mike. And Zaragoza. Here. All right. Okay, so we're going to commence with chapter 3, but before I talk about that, somebody just reminded me, and I made a correction earlier about the due date for assignment 2. So the original date was from last year, that was in the system. I modified it or changed it so that it's due tomorrow, all right? So make sure that you submit it by tomorrow midnight so that I can have it to grade over the weekend and then get back to you as soon as possible. And I think I told you already, and you would have seen that I've emailed you your graded work for assignment number 1, right? So you can use that to review. And I don't remember if hold on, let me check here. If I posted the answer key. Go here. Oh, I didn't publish. Okay, so I need to do that. I'll do that as soon as I'm finished with this class. I'll make sure upload the answer key for assignment number 1 here so that you can have that to review. So when you prepare for your first test, you can use those to help you to prepare that. All right, so let me commence with the discussion about stoichiometry. And again, this is a topic which you would have covered already in your class. So again, I'm going to go through this rather quickly. Just to remind you what stoichiometry is. Stoichiometry is basically that area in chemistry where we're concerned with the quantitative relationships between substances involved in a reaction, right? This, of course, involves, other skills like balancing equations and so on, right? In fact, the very first thing you need to have in order for you to do any stoichiometry type problems is to start off with a balance equation. In some cases, you may be given the balance equation already, and therefore you can start from there. In other cases, you might be given an unbalanced equation, in which case you have to balance it before you can proceed to solve the rest of the problem. And yet in other cases, you might not be given an equation to balance, you might be given a description of the reaction in words, And then based on that, you can determine what the balance equation is, and then you can solve the problem, all right? So, as you're gonna see, there's several things that will be involved when it comes to, stoichiometry. The first thing we're gonna talk about is something that we touched on earlier, the definition of molecular mass, which of course we all know what that is. That is the sum of the atomic masses of all the atoms as represented in the molecular formula. And then, oh, and by the way, the term molecular mass is specifically for molecule, right? Now, for ionic compounds, we use a similar term, but it can't be molecular mass because ionic compounds do not exist as molecules. So the term that we use for ionic compounds, we call it the formula mass, which is basically the sum of the atomic masses based on the formula for the particular ionic compound, right? So please note the difference between the two. Molecular mass is the sum of the atoms, sum of the atomic masses of the atoms as represented in the molecular formula. But in the case of formula mass, we basically do the same thing, but this time it's according to the formula of the ionic compound, right? So for example, if you're asked to calculate the formula mass of ammonium sulfate, which is an ionic compound, the first thing, of course, you need to figure out is what the formula is. You can do it up here. The formula is NH. The formula is NH4 to SO4. And this underscores the importance of knowing how to write the formulas based on the name, right? So that's a formula. And basically all you have to do is consult the periodic table and determine the atomic masses of each of them, add them up, and that's it. So in the case of nitrogen, the atomic mass of nitrogen is 14.01 AMU. And you have to multiply that by 2 because of this 2 here. In the case of hydrogen, it is 1.008 AMU. And in this case, we have to multiply by 2 times 4, 8. And then in the case of sulfur, sorry, that should not be a plus sign. In the case of sulfur, the molar mass is 32.06, I think. Let's see from here. 0.07 actually. So 32.07 ANU. And then for the oxygens, each of them will carry a mass of 16.00. So that would be 16.00 times 4. And then we have to do the calculation. So 14.01 times 2 gives you 14.01 times 2. So this part here gives 28.02 AMU. And then 1.008 times 4 times 8, I'm sorry, gives 8.064 AMU. And then you still have the 32.07 AMU here. And then in the case of oxygen, that will be 64.00 AMU. And then we add these numbers together. So let's see what we get here, 28.02 plus 8.064 plus 32.07 plus 64. And this comes to a grand total, according to my calculation, being equal to, you have to round out to 2 sig figs, so that's 132.15. Now, please correct me if I'm wrong. Do this yourself and see if your answer matches up with what I have. Okay. But that's what I got. Okay, any questions about this? This should be relatively simple, all right? Any questions? Nope. Okay, moving along. So again, some terms that you should have met before. The mole, the concept of the mole and Avogadro's number. I like to look at the mole as a regular counting number, such as, well, like the counting number that we will use in everyday language to describe a dozen, right? Everybody knows 1 dozen is equal to 12. Well, in chemistry and in physics, the mole is kind of like that, excepting that it's a very large number, right? So whenever you hear chemists or physicists talk about the mole, you're talking about this huge number, which is 6.02 times 10 to the 23, right? And that represents the number of items present in 1 mole of literally anything. You can apply it to literally any counting item that you encounter. You can apply it to the number of atoms, you can apply it to ions, you can apply it to the number of people on Earth, whatever, right? But in chemistry, of course, and in physics, we use these terms, or this term, in reference to usually very small particles that exist in huge numbers. Atoms, molecules, ions, and so on, right? Now, the actual definition of the mole is given right here in the first item right here. It is the amount of substance that contains as many elementary entities as there are atoms in exactly 12 grams of the carbon-12 isotope. So that was the definition that was set by the powers that be. I'm not sure if it was IUPAC, but whoever it was, that's what they said, right? By definition, whatever the number of items that will be present in 12 grams of the carbon-12 isotope, that would be representing 1 mole. That substance, the amount of substance will be 1 mole. And that mole will contain this number, which is known as Avogadro's number, right? So 1 mole of anything is equal to basically Avogadro's number of whatever you're referring to. Atoms, molecules, ions, whatever, right? And just to give you an idea as to how huge a number this is, as stated here, 1 mole of oranges would weigh about as much as the Earth. So that gives you an idea as to what a large number that is, right? So, very important concept in fundamental chemistry. One important thing I want to mention here, in terms of abbreviation, we do not use uppercase M or lowercase m to represent the unit of mole, right? Uppercase M represents molarity, which I'm quite sure you'd have encountered before. And lowercase m, well, depending on the context, can represent meters, right, in terms of unit of length, or it can represent another unit of concentration, which is known as molality, which you will not meet in general chemistry 2, but you will meet, you will not meet in general chemistry 1, but if you have to do Gen Chem 2, then you will meet that particular way of expressing or measuring the concentration. Okay, so in terms of abbreviation, in most textbooks, they use MOL, which is not much of a difference between MOL and MOLE, but that's basically the convention that is used in terms of abbreviation, right? Okay, so just to show you the relationship quantitatively of different substances involved in a reaction and how we can apply the mole concept to it, right? So this here is demonstrating at the very top the reaction between carbon and oxygen to form carbon dioxide, right? So based on the information provided here, 1 carbon atom will react with 1 oxygen molecule to form 1 carbon dioxide molecule, right? Now, if we were to multiply all of these by 12, in other words, you have 1 dozen carbon atoms here reacting with 1 dozen oxygen atom molecules here, that will give you 1 dozen carbon dioxide molecule. And then if we continue to increase the relative amounts to 1 mole, right? So 1 mole is 6.02 times 10 to the 23, right? Of each of these, right? Then what we can say is that 1 mole of carbon atoms will react with 1 mole of oxygen to form 1 mole of carbon dioxide. So the point I'm getting at here with this diagram here is that a balanced equation, and we're going to talk about equations later on, but a balanced equations not only represent the relationship between the different substances on a molecular level, right? You can also extend it to the level of moles, right? So when you see an equation like this, you can immediately interpret it as 1 mole of carbon will react with 1 mole of oxygen to give you 1 mole of carbon dioxide, right? So that's basically what that is showing. Another thing that is being shown here is that something we learned in the previous chapter concerning the conservation of mass law. If you remember, we said that in any chemical reaction, according to this law, the total mass of the products will be equal to the total mass of the reactant, right? And you can see that clearly here because 1 mole of carbon atoms will have a mass of 12.011 grams. 1 mole of oxygen molecules will have this mass, and 1 mole of carbon dioxide molecules will have this mass. And if you add the 12.011 to the 31.9988, you're going to get 44.010. So that shows you that matter or mass, or for this matter, atoms are not created nor destroyed as you go from the reactants to the products, right? And therefore, as a result, the masses are conserved as you go from the reactants to the products. Okay, so that's that. So another thing I want to mention here is that when it comes to the mole of anything, right? Let's say you have 1 mole of different substances. That does not mean that they all weigh the same, right? So as demonstrated here, you have different substances. You have sulfur, you have copper, you have mercury, and you have a balloon filled with 1 mole of helium, right? Now, what they all have in common is the number of atoms present, right? They all have Avogadro's number of atoms present, but the masses are different. And the reason why the masses are different is because the masses of the atoms themselves are different, all right? So, as stated here, the question is asking how many atoms of helium are present, of sulfur, of copper, of mercury. The answer is the same for all of them. 6.02 times 10 to the 23, all right? Now, here we're going to get into the relationship between the mole of a substance and what is called the molar mass. And the molar mass is, by definition, what is stated here. It is the mass of 1 mole of a substance. And of course, that number will be different as you go from one substance to the other. At this juncture, I want to say to you that when it comes to the value of the molar mass, it turns out that it's equal to the atomic mass if you're dealing with an element, the molecular mass if you're dealing with molecules, or formula mass if you're dealing with ions, right? So numerically speaking, the molar mass is the same thing as the atomic mass, molecular mass, or formula mass. However, the difference would be in the units when they're expressed, right? The units of molar mass is always grams per mole, while the units of atomic mass, as we learned earlier, is AMU, right? So the molar mass is expressed in grams per mole, but the atomic mass, or the molecular mass, or the formula mass is expressed in atomic mass units. So just to give you a couple of examples, if you take the sodium atom, its atomic mass is 22.99 AMU, but the molar mass is 22.99 grams per mole, all right? Another example, in this case, a molecule, the molecular mass of carbon dioxide is 44.01 AMU, but the molar mass of carbon dioxide is 44.01 grams per mole. And I think I have one more example lined up here. Oh, this is an ionic compound. So the formula mass of potassium chloride is 74.56, but the molar mass is 74.56 grams per mole. So AMU in the case of formula mass, grams per mole in the case of molar mass. Okay, so that's basically the relationship between the molar mass and the mole, and the relationship between the molar mass and the atomic mass, molecular mass, or formula mass. Okay, so basically, because of these equalities that we can establish, basically we can do certain calculations where we can convert from one particular unit to another. So we can convert from, let's say, moles to the number of atoms. We can go from the number of atoms to the molar mass or the grams, or we can go from grams to moles or moles to grams. There are different ways of doing different conversion, right? So just to give you a few examples based on the relationship shown here. So one conversion factor that we can use is 1 mole of sodium divided by 22.9 grams of sodium, or we can flip it where we get the mass in grams of sodium above and 1 mole of sodium below. And then here is a relationship between 1 mole of sodium and Avogadro's number, right? Or we can have a relationship between Avogadro's number and the grams of sodium. That's not shown here, but that's another example of a conversion factor that we can derive from the expressions given here, right? And of course, as always, when it comes to these types of problems, you may have to do some preliminary calculations to get to the particular unit that you want to convert from to whatever unit you're asked for. And even after that, there may be also some follow-up calculations after that step. So we're going to see some examples of that shortly. But before we get to those examples, another way of interpreting the formula of a compound, right, is in terms of the moles of atoms or ions present per mole of the compound itself. So just to use this example here, 1 mole of this compound, the formula is C3H8O3, right? Now, in terms of the composition or the different substances, or I should say specifically the different elements that are present within this compound, we can break it down to say, okay, because we have a subscript of 3 here, that means that 1 mole of this particular compound will have 3 moles of carbon, and 8 moles of hydrogen because of this subscript here for hydrogen, and 3 moles of oxygen, right? So we can actually establish a relationship between the mole of the compound and the moles of each of the different elements present in the compound based on the formula. And here's a more complex example, but it's based on the same idea. If you have 1 mole of ammonium sulfate, you can break this down into 2 moles of ions, of ammonium ions, and 1 mole of sulfate ions. Again, depending on whether or not that's what the question is asking for. And then you can break this down even further, right? Because if you look at the formula here for the ammonium ions, right, it's NH4, right? And there are 2 moles of these. So therefore, you can break this down to say that in 1 mole of ammonium sulfate, you're going to have 2 moles of nitrogen. You're going to have 2 times 4, 8 moles of hydrogen. And then as far as the sulfate part is concerned, you're going to have 1 mole of sulfur atoms and 4 moles of oxygen atoms. So basically, if you're given a formula for a compound, you can establish the relationship between the moles of the compound itself, based on the molecular formula, and the number of moles of the different elements present within the compound, right? Okay, so let's look at these examples right here. And what I'm going to do is copy and paste this onto a Word. Okay, so this question has several parts. It says determine the mass of a 0.0750 mole sample of sodium. So let's do that part first. So what I would do is I would start off with the 0.0750 moles of sodium. And the question is asking for the mass. So this would be equal to how many grams of sodium? That's basically what the question is asking. So start off with what we're given. Moles of sodium. And then I'll multiply by a conversion factor, which allows you to convert from moles of sodium to grams. And that would be the molar mass, right? So you consult the periodic table, you look at the molar mass of sodium, and the molar mass of sodium is 22.9 9 grams per mole, I think, of sodium. So the way we would set this up here is that I would put 1 mole of sodium below and 22.99 grams of sodium above. And that's it as far as the setup is concerned. So 0.075 times 22.99. And according to my calculation, this works out to equal to 1.72 grams of sodium. And that's it. That's how you solve that problem. All right. Any question about this? Questions? Okay, so the next question is, you want to get, they gave you the grams of sodium and you want a number of moles, right? So in this case, you're starting with 62.5 grams of sodium and you want to find the number of moles. So basically, this is the reverse of what we just did in A. We're going to start off with 62.5 grams of sodium, and then we're going to multiply that by 1 mole of sodium above, and below will be the molar mass, right? That's how you set it up, of sodium, because you want this to cancel out with this. So again, we're going to do the number crunching. And According to my calculation, rounding up to 3 sig figs, the answer would be 2.72. 2.72 moles of sodium. And that's how you do that. All right. So that's basically the B part. Any questions about this? Questions? Questions? Okay. C part. They gave you the number of atoms. You know what you need? Clear this place. You can do all this place. Okay, so in the case of the C part, they gave you 1.00 times 10 to the 25 sodium atoms. And you're asked to find out the mass, presumably in grams of sodium, right? Now, in this case, it's a bit more complicated because you cannot get from atoms to grams unless you include Avogadro's number. So basically, you're going to start with the number of atoms first. Then you're going to convert that to moles using Avogadro's number, and then you're going to convert that to grams. So basically, to get from atoms to grams, you're going to need a series of 2 conversion factors. So we're going to start off with 1.00 times 10 to the 25 sodium atoms, and we have to multiply that by conversion factor, which includes Avogadro's number, where you have 1 mole of sodium above, and below you're going to have 6.02 times 10 to the 23 sodium atoms below, right? So that this unit will cancel out with this unit, right? So up to this point, we would have determined the moles. So the next conversion factor is where the molar mass comes in, right? To convert from moles to grams. So down here, you're going to have 1 mole of sodium, and up above, you're going to have the molar mass of sodium, which is 22.99 grams of sodium. And that's it. So you're going to have 1 times 10 to the 25 divided by 6.02 times 10 to the 23 times 22.99. And according to my calculation, when rounded off to 3 sig figs, the final answer becomes 382 grams of sodium. And that's basically how you do the C part. All right, any questions about this? Any questions? Okay, so the next question is asking for, in the case of D, the mass of a single atom, all right? The mass of a single atom. How shall we approach this? Well, a couple of things we need to keep in mind. We need to keep in mind that the molar mass of sodium is equal to 22.99 grams per mole, right? And we know that 1 mole is equal to 6.02 times 10 to the 23 atoms per mole, right? So basically, if you want to find the mass of a single atom, what we do is divide the molar mass by the mole, or by the number of atoms per mole, right? So in other words, 22.99 grams per mole will be divided by 6.02 times 10 to the 23 atoms per mole, right? So the mole units will cancel out, and whatever you get will be the mass in grams per atom. So 22.99 divided by 6.02 times 10 to the 23, and according to my calculation, this works out to be equal to 3.82 times 10 to the minus 23. And that would be the mass of each atom, which of course you'd expect to be a very small number, right? Okay, any questions about the last one? D. Questions? Questions? Okay, so let's go back to the PowerPoint and see what's next. You know what? Before we even do that, let me start you off on assignment number 3. So Go. Here we go. It's for you. It's for you. Keep on pass down. Keep on pass down. That's for you. And there's you. All right, so, oh, and for you guys out there in Zoom, let me check and see if I have published this particular assignment. Okay, so let me go here. Here. Assignment. Number 3. Okay, so I'm publishing it now, folks, for you guys out there in Zoom. And while I'm at it, let me just bring it up on the screen. Okay, so what I want us to focus on are question 1. Okay, 1. Can't do 2 yet. All right, so let's see if we can solve these together. It says complete the following conversion, and the first one is moles of 0.00515 grams of water. So let me hear your ideas as to how we can solve this. Let me turn on my pen. Okay, so any ideas as to how we can go from 0.00515 grams of water to moles of water? So let me write this down here, 0.00515 grams of water. What would you H2O, what would you multiply that by in order to go from grams to moles of water? In other words, what would go up here as the numerator, and what would go down here as the denominator?
The mole would have to go on the bottom,
The mole goes where?
on the bottom. Oh, I'm sorry, on top.
Exactly. And in fact, it should be 1 mole of H2O, right?
Yes,
And what goes down here?
the gram.
The grams, right? How do we get the grams? You have to go to the periodic table and you look up the molar mass of hydrogen and oxygen. And it would be, for hydrogen, it's 1.004 times 2. And then you add to that 16.00. So you're gonna get oh, wait a minute. What did I say? 1.008 times 2 plus 0.6. Okay, so you're gonna get 18.02 grams. And that's it. As far as the syllabus is concerned. So it's 0.00515 divided by 18.02. And according to my calculation, rounded off to 3 sig figs, the answer is 2.86 times 10 to the minus 4 moles of H2O. All right, so that's how we do the A part. Any question about this? Any question? Questions? Okay, what about the B part? Now, in the case of the B part, you have to be careful. Because in the case of the B part, they gave you the moles of sodium hydroxide and they're asking for the number of atoms, right? They didn't specify atoms of what. Basically, what they mean is all atoms, right? So, we're gonna start off with 3.50 moles of sodium hydroxide. So what would be your first step? You're gonna go 1 mole of sodium hydroxide below. And above you're gonna have what? Okay, 6.02 times 10 to the 23. And I'm gonna put your formula units. Right, because remember sodium hydroxide is an ionic compound. So you won't have molecules present, instead you have formula units, all right? Then what would be the next conversion factor you think? So, by the way, this will cancel with this, all right? So you will have with formula units. Now remember what the question is asking for. The question is asking for how many atoms, right? So, how many atoms would you expect to be in one formula unit? In one formula unit of sodium hydroxide, how many atoms total would you expect to be present based on the formula? I'm sorry? Five, no? I'm sorry? No, 3.5 is the moles given.
Would it be like 2 or 3?
It has to be a one number, you have to just store it. Alright. 3, exactly. Sodium, oxygen, and hydrogen, right? So therefore, 3 atoms will be present per formula unit. So this unit will cancel with that unit, and then we do the calculation of 3.5 times 6.02 times 10 to the 23 times 3. And according to my calculation, I got 6.32 rounded up to 366 times 10 to the 24 atoms. Right? And that's how that is done. Any questions about this? Any questions? Questions? No questions? Any questions out there in Zoom? Okay, is it okay for me to clear all this? Okay, so let me do that. Scroll down. Okay, so for C, they gave you 2.50 moles. They gave you 2.50 moles of oxygen, and they're asking for the mass in grams of oxygen, right? So you're going to start off with 2.50 moles of O2. So my question to you is, what would you multiply that by in the conversion factor? What would be at top in the numerator, and what will be below in the denominator? 16, why 16? Hint.
Oh, you have.
32. 0.00 grams of O2. Is there anybody here who have me for intro? You? Okay. I always stress that there are certain molecules, I think we're going to meet them later on, but you should have learned this in your intro. There are certain compounds that exist as diatomic molecules, right? You need to memorize them. Oxygen, nitrogen, hydrogen, and the halogens, fluorine, chlorine, bromine, and iodine, right? So whenever you see a question which talks about oxygen or chlorine involved in a reaction, need to remember that those gases exist as diatomics. And then phosphorus is kind of unusual because phosphorus exists as P4, right? And sulfur is another unique one. It exists as S8, right? So if you had me before, you should remember, because I remember stressing it to that. And for those of you who are having me now as your instructor, please remember that those gases exist. Let me write it down just to remind you. Oxygen, hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. Remember these folks as diatomics. And then you have P4, and then you have S8, right? So please remember those compounds, or I should say those elements that exist as molecules. All right. So that was important with respect to the O2 here, because the molar mass of O2 is not 16, it's 2 times 16, which is 32.00 grams per mole of oxygen. All right. So This will cancel out with that, so let's see what this gives. 2.5 times 32.00, and according to my calculation, basic fix, according to my calculation, that would be 0.800 grams of O2. I did something wrong. Oh, sorry, this should be 80, not 80. My bad, my bad. This should be 80.00, 80.0, well, 0.0, basically, grams of O2. Okay, very good. Any questions about this? Any questions? Any questions? Questions? All right, so let's hear what you have to say about this one. I'm going to try to help you as little as possible. I'm going to start you guys off with this one. You're starting with 10.5 grams of C6H12O6, right? And you want to get the equivalent number of carbon atoms. All right, so 10.5 grams of C6H12O6. So my question to you is, what would be the first conversion factor? And let me just say, there's going to be more than one conversion factor. So what would be the very first conversion factor you would use in order to answer this question? Yes, ma'am.
Grams to moles.
Okay, so what would go above here?
1 mole.
1 mole of
Uh,
C6H12O6.
Yeah.
And down here would be the,
grams.
right, so can somebody add up 6 times, let me do it. 6 times 12.01 plus 12 times 1.008 plus 6 times oxygen, which is 16. Okay, so correct me if I'm wrong, but this is what I got. I got 180.16 grams of C6H12O6. That's what I got, right? Okay, so this will cancel out with this. Now remember, the question is not asking for the grams or the moles. It's asking for what? The number of carbon atoms. So far, we have the moles, right, of the C6H12O6. So the next question is, what will be the next conversion factor? Now that we have the moles of the compound, what's the next step? Moles to atoms. Okay, if you're going to do it that way, you're kind of jumping a step, but if you want to do it that way, so how would you get from moles? 1 mole of actually, this is actually will work out. So you want to go from moles to atoms. Now remember, the question is specific about atoms, right? Right? So if I were to put 1 mole of C6H12O6 down here, what would go up top here? Okay, but remember now, you have to take into account that there's a 6 right here. And this is the reason why I would prefer to go stepwise. So let me do that, right? What I would do here is that in the numerator, based on the formula here, I would put 6 moles of carbon. Right? And then now, to what he said, Avogadro's number would come into play. 1 mole of carbon will be equal to 6.02 times 10 to the 23 carbon atoms, which is what the question is asking for. So that's the reason why I prefer to do it stepwise, right? So this will cancel out with this will cancel out with that, and then we do the number crunching, 10.5 divided by 180.16 times 6 times 6.02 times 10 to the 23, and this is what I got, rounded off to 3 sig figs, 2.11 times 10 to the 23 carbon atoms. And that would be the answer that the question is asking for. Okay, any question about this one? Any questions? Questions? Any questions? Alrighty, I think that's it for question number one. I don't think we can do any other assignment. Questions now, so then we go back to PowerPoint. Okay, so now we're gonna get into how we calculate the percent composition of different elements in a compound. And it's a very simple concept actually. So the definition of mass percent composition of a compound is in reference to the mass of each element present per 100 grams of the compound. So there are two equations we can use to calculate that value. One way is dividing the mass of the element present by 100 grams of the compound that has that mass, and that will give you the percentage of that element present in the compound. Or we can simply take the mass of the element per mass of the compound and times 100, and that will give you the percentage of the element present in the compound. And of course, if you were to determine the percentage of each element present in the compound, when you add them up, you should get what? 100%, right? So that's basically what the mass percent composition is all about. So if you were to calculate the percent composition of this compound, butane, the way you go about it is very simple actually, is that, this is the formula for butane right here, right? So to get, what we need to do first is find the total molar mass of the compound, right? So 4 times 12.01 grams per mole plus 10 times 1.008 grams per mole. So let's find out what that gives first. So 4 times 12.01 plus 10 times 1.008. So according to my calculation, this works out to be equal to 58.12 grams per mole, right? Now to find the percentage of carbon present in butane, we have to take into account that there are 4 carbon atoms represented in the molecule. So we're going to take 4 multiplied by the molar mass of carbon, which is 12.01 grams per mole, and then divide that by the total molar mass of the compound, and multiply all of that by 100%. And let's see what that gives. 12.41 times 4 divided by 58.12 times 100. And according to my calculation, this works out to be, when we round it off to 466, 82.66%. All right. And then we do a similar calculation in the case of the percentage of hydrogen. Well, in this case, you have 10 of them. So that would be 10 times the molar mass of hydrogen, which is 1.008 grams per mole, divided by, again, 58.12 grams per mole. So let's see what that gives. 10 times 1.08 divided by 58.12. And according, times 100, can't forget that. So according to my okay, I did something else. Okay, I see what I did. I see the mistake I made. Times 100. So according to my calculation, this works out to be equal to 17.34%. And that's basically how you calculate the percentage composition of butane. And of course, when you add these two, the 82.66 plus the 17.34, you should get 100, which is what is the result. In some cases, you may get a number close to 100. Like you may get something like 100.05 or something like that. That's fine, all right, because when you're doing these calculations, you know, sometimes errors are introduced, which results in the number or the final answer here, when you add them up, deviating somewhat from what it should be. All right, any questions from about this question? Any question about this? Okay, so what comes in mind? Okay. So let's continue. So basically, let's do these examples here. We copy and paste these. These are basically asking the same thing. Oops. Okay, so let me go back to the Word. And let me, there it is. All of this. We also get rid of. Okay, what did I do wrong? Keep doing it. Okay, so the first part is asking for you to calculate the four significant figures, so they're specific about this. The mass percent of each element in ammonium nitrate. So the first thing you need to do is write down the formula of ammonium nitrate. So can anybody tell me what the formula for ammonium nitrate is? I'm gonna call this A, I'm gonna call this B. Okay, so what's the formula for ammonium nitrate? And when it comes to writing down the formulas, especially when it comes to ion compounds, you might find it useful to use the tables that is provided in Canvas, especially the parts of the table which lists the common ions, right? So what I would do is consult the table, and I will look for the formula for the ammonium ion, and I will look for the formula for the nitrogen ion, right? So what's the formula for the ammonium ion? NH what? NH4 plus, right? And what's the formula for the nitrogen ion? NO3 minus, all right? So what's the formula for ammonium nitrate? NH4, NO3, right? So now the question is asking for you to find the mass percent of each element present, right? So basically, we have to find the percentage of, well, first we have to find the molar mass. All right, so how do we find the molar mass? We have two nitrogens, right? So that will be 2 times what for nitrogen? What's the molar mass of nitrogen? 14.01, right? Grams per mole, right? So there are 2 of them. And then we're going to find for hydrogen, there are 4 of them. And the molar mass of hydrogen is 1.008 grams per mole. All right. And then we're going to add 3 times, continue down here, 3 times the molar mass of oxygen, which is what's the molar mass of oxygen? 16.00 grams per mole, right? So let's do the number crunching. 14.01 times 2 plus 4 times 1.008 plus 48, which is 3 times 16. So according to my calculations, this works out to be equal to 80.05. 80.05 grams per mole, all right? Then we need to find the percentage of each of them, right? Now in the case of nitrogen, that percentage would be 2 times 14.01 grams per mole divided by the 80.05 grams per mole times 100%. Screw up. All right. So let's see what that gives. 14.01 times 2 divided by 80.05 times 100 So according to my calculation, this works out to be equal to 35.00%. And then we do a similar calculation for the hydrogen. That would be 4 times 1.008 grams per mole divided by the same 8.05 grams per mole times 100%. So let's see what that gives. 1.008 times 4 divided by 80.05 times 100. And according to my calculation, this works out to, again, 466, so 5.037%. All right. And then in the case of the oxygen, percent oxygen, we take 3 times 16.00 grams per mole, again divided by the 80.05 grams per mole times 100%. So that's 3 times 16 divided by 80.05 times 100. And according to my calculation, this works out to be 59.96. Now, what I like to do when it comes to these problems is add them up to see if it comes up to 100, which basically says that my answers are valid. So what I'm going to do now is add 35 to 35 plus 5.037 plus 59.96. And I got, when I did that, I got 99, pretty much 100%. All right. I got 99.997%. So that's 100%. So I'm fairly confident in these results, right? So that basically answers the A part. All right. Any questions about this? Any questions? All right. So let me clear this so I can get some more space to work with. In fact, now the reason why I'm just clearing the top part here is because I actually will going to need this here in order to answer the B part. Now the B part is asking how many grams of nitrogen are present in 46.34 grams of ammonium nitrate, right? Now, so they gave you 46.34 grams of ammonium nitrate, right? And they want to find out the mass in grams of nitrogen. What you can do is use this number here, because this number gives you the mass of nitrogen for every 100 grams of the ammonium nitrate. So we can actually represent that as a conversion factor. 35.00 grams of nitrogen divided by 100 grams of ammonium nitrate. And that's it. This will go with that. Let's see what this gives. 46.34 times 35 divided by 100. And according to my calculation, this works out to be equal to 16 point, what is it? 0.22. 16.22 grams of nitrogen present in this much ammonium nitrate. All right. Okay, any questions about this one? Any questions? Questions? Okay, so continuing. Let me see here. Oh. What is that? Okay, so. Okay, so we're gonna go back to the PowerPoint here and see what comes up. In fact. Oh. Let me check out the assignment. Okay, so in the assignment, right? If you understood what we just did in the example that I just worked, then you should be able to do question number 2. Okay, right. Question number 2. So I'm gonna leave that for you to work on, right? Again, if you have any problems, let me know, right? But basically, it's the same idea as I showed you just now in the examples from the PowerPoint. So let me go back to the PowerPoint. And let's talk about getting the chemical formulas. And should I start this now? Okay. Let me start this now. Okay, now what we just discussed is problems where you're given the formula and you're asked to find the percentage of each element present. That is relatively easy. What is more challenging is the reverse, where you're given a percentage of each element and you're asked to find out what the formula is, right? Now, in order for us to do this, as you're gonna see, basically, what you have to do first is find out what the empirical formula is, right? And if you remember, the empirical formula is basically the formula that gives you the simplest ratio of all the atoms that are present, of the different elements present in a substance, right? And then once you find the empirical formula, the next step would be to find the molecular formula. And in order for you to find the molecular formula, you're gonna need some additional information. So we're gonna see examples of this in this section, right? So, as I said before, we can reverse the process, but it's a bit more challenging. Because what we have to do first is find the moles. And that is based on whether or not the question gives you the masses or the percentages of the different elements. And then what you have to do next is find the smallest whole number ratio of the moles of the substances involved, and those numbers will end up giving you the subscripts in the empirical formula. So the best way to learn this, of course, is to go directly into examples. So I'm going to copy this one here first and post it in Word. Okay, so what I'm gonna do is, well, let's read the question first. The question says, phenol, which is a general disinfectant, has a composition, and they give you the data for the different percentages of each element present. And the question is asking for you to find the empirical formula. All right, now the way I like to do this, I like to do this in a tabular form, right? So I'm going to construct a table where at the top, I'm going to put the carbon, hydrogen, and oxygen. And the first step is to determine the masses of each element present. Now, they did not give us the masses. What they gave us were the percentage by mass, right? So what we can do is we can assume that we're working with 100 grams of a substance. If we make that assumption, that means that those numbers that you see here would represent the mass in grams of each element present per 100 grams of the substance, right? So the first row here would be the masses, and the masses will simply be 76.57 grams of carbon, 6.43 grams of hydrogen, and 17.00 grams of oxygen, right? So we get these numbers by simply assuming that we're working with 100 grams of the substance, and therefore those percentages would represent the mass in grams of each element present per 100 grams of the substance, right? The next step is to find the moles of each element, right? And by now, we know how to do that. Basically, to find the moles, we divide each of these by their respective molar masses, right? So in the case of carbon, it's 76.57 grams multiplied by 1 mole over 12.01 grams. In the case of hydrogen, it's 6.43 grams multiplied by 1 mole over 1.008 grams. And then finally, in the case of oxygen, you're going to take the 17.00 grams and multiply that by 1 mole over the molar mass of oxygen, which is 16.00 grams, right? So we need to work out each of these. I'm going to start with the carbon, 76.57 divided by 12.01. So according to my calculation, this works out to be equal to 6.376 moles, because the grams will cancel out here and here. In the case of hydrogen, that's 6.43 divided by 1.008. And according to my calculation, this gives 6.37. Okay, what am I saying here? 9 moles. Again, grams will cancel out here and here. And then finally, in the case of oxygen, it's 17.00 divided by 16. And according to my calculation, this works out to be equal to 1.06. So 1.063 moles. Again, gram units will cancel, right? So that's what we do at this step. We simply divide each of them by their respective molar masses. The next step is to find the simplest ratio. So how do we find the simplest ratio? What we do is we look at the mole values here and decide on which one is the smallest one. And then we divide all of them by that value, right? So the smallest value here is the 1.063 moles. So we're going to divide all of these by that value. When you divide this by itself, you're going to get 1, right? So in the case of carbon, it's going to be 6.376 moles divided by 1.063 moles. And let's see what that gives. 6.376 divided by 1.063. And according to my calculation, this gives 5.998. Rounded off to 468. I'm going to do the same thing here for the hydrogen. I'm going to divide the 6.379 moles by the 1.063 moles. And let's see what that gives. 6.379 divided by 1.063. And according to my calculation, put it down here, that will equal to 6.001. All right. So that's what we get when we divide each of them by the simplest, or I should say the lowest mole value, to get the simplest ratio. Now, if you'll notice here, these two numbers are very close to 6, which is an integer, which is ideal, and which is what we want, because those integers will serve as the subscripts in the final empirical formula. So all we can say here is that this is approximately equal to 6, and this is approximately equal to 6, and that is 1. So therefore, the empirical formula is equal to C6H6O. And that's how you get the empirical formula in this case, right? Any questions? Any questions about it? All right. Now let me just say that the other question is a bit more complicated because it adds an extra step, which is required in this situation. But I'm going to stop here. And then next class, we're going to pick up with the next question. Now, based on what we have done as far as the empirical formula is concerned, you should also be able to do let's see, number 3A, 3B, 3C. All right, yes. So try the questions in number 3 as well. All right. Again, if you have any problems, please contact me so that you can get them. All right. Let me get those students who came in late. Is Aleo Ligaris just in here?
Yes.
Francois? Leave it?
Here.
Summons? White? Okay, that's good. I'll see you guys on Tuesday.
Professor,
Oh, I need to make an announcement about that, because I think it is about starting next week.
Yeah.
Yeah, I'll put it off until, maybe the week after. I'm going to post an announcement about it.
Is it possible to take it next week? Cause I won't be there.
Oh, you want me to get it following week?
You know.
Maybe not, but you can take it when you get back. Right, exactly. All right, no problem.
I did send you a Canvas message.
Yeah, I haven't checked my email yet. I'm gonna go upstairs and. Okay, and for you guys out there in Zoom, I'll be signing off right now.